previously, we saw that for an K algebra R, we got an R module, which is the module of differentials of R over K. And then we obtain a sheaf on spec R just by putting the tilde over this. And we already saw this has some promising properties. So for example, its fiber at a given point is just a cotangent space to that point in the variety. The problem is that when X is any variety, now we still want to define what this sheaf does. And we don't really want to go this route of covering the variety with spectra and then trying to glue those things by hand. It would be much cleaner if we find a second construction of this thing which works globally, which just works for any variety X, and which gives the correct thing back when X is equal to spec R. So this is our goal, and this alternative construction will be motivated by the following lemma. So here we are going to see a second way of defining the omega R module. And this is the following. So R is a K algebra, then we can consider a map delta from R tensor over K with itself to R, which is the easiest map that you can imagine. It just takes F tensor G and sends it to F times G. It's just a thing which expresses that multiplication is linear in both components. So we can get this map, and then we set J to be the kernel of this map. Then the claim is that if we take this J modulo its square, then as R modules, this is isomorphic to omega R. Okay. So this would be a second construction of this omega R. So from this is not yet clear why this is better than the other one, but we're going to see that this naturally comes from a construction which makes sense for any variety X. So for now, we just proved the lemma. An important first question that you can ask here is that I say here J modulo J squared, this is isomorphic to this SR modules. And at this point, you can ask, like, what is the exact R module structure that we put on here? Because the problem is that, so this J lives inside this tensor product. And the claim is this tensor product is an R module in two different ways. Namely, if you have an element of R and you have, for example, such a pure tensor here, then if you want to multiply this, you can either put this A in the first factor, or you can let A act by multiplication in the second factor. And the important thing here is this really matters which one you do, because these things are actually different R module structure. And this comes from the fact that this tensor product here is a tensor product over K. So it's not allowed to just say, well, this A, well, you can pull it over to the other side because A is in R, the tensor product is only over K. So when A happens to be in K, then these two things are the same, but in general, they're different. So there's two different R module structures. For now, we just keep this in mind. We move on for now, but somehow we will have to show that basically later when we look at J modulo J squared, they give us the same thing. Okay. And so the next question we should try to understand what this J squared is. And here we really need to pay attention that how the elements of J actually look, right? So somehow J squared by definition is just take the products of one element in J, another element in J, and then take the module generated by this. So here, and I think Gatman is not entirely precise at this point here. So if you want to write an element of J squared, you should just write two elements of J and then multiply them. Say what you mean by the multiplication. And in general, the elements of J, these are elements of this tensor product, and they don't have to be pure tensors. In general, they can be sums of pure tensors. So somehow one element like this could be the sum from I equals 1 to n, and then you have an F1i tensor G1i. This could be an element in this tensor product. And then, okay, I mean, saying that this lives in J just means that somehow if you sum the F1i times G1i, then this is 0. This is the image of this under this map. So this could be one element. Sorry, this could be one element in J. And then another element in J could be of the similar form, but now we have a different variable. So these could be two elements here. And then multiplying them, I mean, there is a unique way to multiply things, namely it's just component-wise multiplication in this tensor product. So if you multiply these two things, then you get a sum over both I and j running through their respective indices, and then you multiply component-wise, so you get f1i times f2j tensor g1i times g2j, like this. So this is j squared. And the first important observation is, in fact, you can even just write kind of curly brackets here. So somehow this is the set of all such product, and it automatically becomes a submodule of R tensor over K with itself. And this is a submodule with respect to either R module structure above. So it doesn't matter if you multiply in the first component or the second. If you take an element here and multiply by some A, well, then this draws in like this, either in the first component or the second one, but then you can just put this A in either the first component here or the second component here. This is both fine. And somehow, even though there's two different structures, this set is well defined for both of them, and it's a submodule. And so now we want to approach this problem of what is this j modulo j squared? Well, certainly we can form. So we can form this j modulo j squared, and this, for example, first as abelian groups. This is well defined, this quotient, and there's two potentially different R module structures now. Because we could either multiply in the first component or the second one, but the claim here is that these structures are the same. So we can choose either one. And the proof is just a short calculation. So what do we want to understand? So if we had H in R that we want to multiply with, and we have an element psi, which is the sum, again, such a mixed tensor, an element in J, like this, then this, I mean, its equivalence class is an element of this quotient here. And so there would be two different ways to define what H times psi is. And we'll just take the difference and show that this difference is in J squared. This means that in the end, it doesn't matter which one we take. So we have this sum here. And then, well, we can either multiply this H in the second coordinate, then we get fi tensor h times gi, or we can multiply in the first coordinate and we get h times fi tensor gi, like this. So just for emphasis, so somehow this is h times psi, this is h times psi, but this times now means for the two different R module structures. So basically this is a times 1 and this is a times 2. These would be the two different possible structures above. But then in this sum here, we can stare at this for a bit and see that this actually factors as a product of the original thing, fi tensor gi, times 1 tensor h minus h tensor 1. Just because, I mean, if you multiply this thing out, then this times the sum gives the first part, and this times the sum gives the second part. Okay, but now let's just stare at this. This here was the original element psi, which by assumption is in J. And on the other hand, this element I claim is also in J. Now remember, J is just the kernel of this map, taking f tensor g and mapping to f times g. So why is this in this kernel? Well, if you take this, you'd apply delta, then you get 1 times h. If you take this, then you get h times 1. If you take the difference, you get 0. So this is indeed in the kernel. This is indeed this is indeed in J, like this. And so the entire thing is in J squared. And so these two structures are indeed the same. This means that we can get a canonical R module structure by taking either one of them. And then we just checked it with this R module structure. These two things are isomorphic. So this J modulo J squared and the omega R. And for this, we just give maps in the two directions. So one is take the equivalence class of such an element. And then send it to an element of omega R. The correct element to take is fi times dg. Right. And then take the sum over these things. So this is certainly something that you can do. The map in the inverse direction takes one of these symbols df and sends them to a particular element here, namely 1 tensor f minus f tensor 1, like this. And then this, you just check by hand that these are indeed inverse things. So here the same argument at the value above now implies that this thing here is an element in J, and so you can take its representative or its equivalence class in this quotient. Okay. So this was the proof of this lemma, that basically we have a second construction of omega R as such a quotient. And then we can now say for an arbitrary variety X, how do we find a global construction which gives this result? Well, we look at the diagonal delta X inside X cross X. This is now the cross over spec K, so usual times that we already know. So since X is a variety, this is a closed subvariety. And in particular, somehow diagonal is just the same thing as taking kind of 2 times the identity. And so this thing then becomes a closed subscheme. And we have seen if you have a variety and a closed subvariety or scheme and a closed subscheme, then you can get the ideal sheaf of this closed subscheme, which is a sheaf on X cross X. So we get a sheaf on here. And the claim is now what happens when we are in the affine situation. When X is spec R, then this morphism I here, this is 2 times the identity. And we know then X is affine and X cross X is just the spectrum of R tensor over K with R. We saw that the fiber product over K for such affine varieties is just the same as the spectrum of the tensor product of their associated rings. And then this map from spec R to spec R tensor over K with R in this direction comes from a map of rings in the other direction. And this map of rings is exactly delta above. And if you want to verify this, you can go all the way back to the video 12.14, where we constructed this identification. Just observe that delta of F tensor G is, well, the identity map that we're interested in here applied to F times the identity map applied to G. Okay, so this is the connection. Somehow the diagonal morphism in these affine charts looks like this. And then we now want to make this comparison of like what does this ideal sheaf have to do with the J, the kernel of this map delta that we had above? Well, we just observed that there is an exact sequence of R tensor over K with R modules. Just this mapping by delta here, this becomes an R tensor over K R module just by basically, if you have A tensor B, and then this acts on R by just multiplying by A times B. Okay, this is then the modular homomorphism, this is the kernel. So this is the exact sequence of such modules. And on the other hand, by definition, the ideal sheaf J was defined as the kernel of this map here, which is the map induced by this I. And this gives then an exact sequence of O X cross X modules. And we see somehow these things have the property, this is the module associated to this, or this is the sheaf of modules associated to this module. This is the sheaf of module associated to this module. And so this implies that this here is also the sheaf of modules associated to J. This was the statement that we can check the exactness of such a sequence of sheaves which are just the mi tilde, just from the exactness of the corresponding modules. Okay, so this is this relates this curly J sheaf to the usual J module. And then also taking squares and taking quotients is compatible with this tilde operation. So this, which again kind of basically says that you can check exactness on the module level. And so this taking this quotient sheaf here, curly J modulo curly J squared, is just the module associated to this thing here on X cross X. So this is an equality of O X cross X modules. And if you now pull this back under this I, under the I, then you get here remember the pullback doesn't change the module, it just changes which ring we use. And so in this case we use R as in the ring. And this shows this equality here. So somehow this pullback is just the module associated to J modulo J squared. And this is where we make the final connection, namely J modulo J squared as an R module is isomorphic to omega R. Okay, so this was a long trip, but somehow what this shows is that this j modulo j squared, which makes sense on all of x cross x, that if you pull this back under the diagonal, you get back this this omega r on each spec of r inside x. And so when x is any variety, you just define omega x, the cotangent sheaf of x, as take this j modulo j squared and pull it back. This gives you some sheaf. And what this lengthy computation here just checked is that on spec r inside x open, this just restricts to the omega r tilde. And this is perfect because somehow we know that on this thing, the cotangent sheaf should be this. And so we have now constructed something in an abstract way, which gives us the right thing. And then all these D maps, which go from O spec R to the omega R tilde, these all glue together then to give a map of sheaves from OX to omega R. This is kind of the differential. And this is a map of sheaves, again, is not a morphism of OX modules. And so this is the fully general definition of the cotangent sheaf. And then in the next video, we're going to see that we can now make a connection between the property of X being a smooth variety and the property of this sheaf being locally free.